Today we're diving into the hidden world of gases. We're on a hunt for a single, super powerful number that basically explains everything about how they behave. So have you ever noticed this? You're outside, the sun hits a helium balloon, and poof, it's warm instantly. But the air around you, it takes way longer to heat up. It seems like a simple little thing, right? But the answer? Well, the answer gets us right down to the nitty-gritty of how different gases handle energy. It's a great little mystery to kick things off.
And the key to solving this mystery isn't just knowing that molecules are, bouncing around like crazy. It's about how they're moving, the different ways they can bounce and tumble and even stretch. That secret hidden motion, that's where all the action really is.
And that right there brings us to the hero of our story today. It's a concept called degrees of freedom, and we're just going to call it F. Honestly, the best way to think about it is like a count of all the secret dance moves a molecule can do. And every single one of those moves is a way for it to hold on to energy. So what are these so-called dance moves? Well, they basically fall into three main types. First, you've got translation. That's just the molecule moving from point A to point B. Simple. Then there's rotation, where it's tumbling end over end. And finally, you have vibration. This is where the atoms inside the molecule are stretching and compressing their bonds, almost like they're connected by a tiny spring.
Okay, to really wrap our heads around this, we're going to build it up from scratch. We'll start with the absolute simplest molecules you can imagine, and then work our way up to the more complicated stuff.
All right, first up, a monoatomic gas. Think of the helium in that balloon we started with. Monoatomic just means it's a single atom, all by its lonesome. The easiest way to picture it, just imagine a tiny, perfect billiard ball floating around in space. So how can this little billiard ball move? Well, it can only really do three things, right? It can move forward and back, that's one. Left and right, that's two. And up and down, that's three. So it has three ways to move. That means its degree of freedom, its F value, is exactly 3.
Okay, let's level up. Case number 2 is a diatomic gas. Now this is most of the air that you and I are breathing right now. Think oxygen or nitrogen. Diatomic just means two atoms bonded together. The go-to image for this is a tiny little dumbbell.
So it still has those same three ways of moving through space, the up-down, left-right, forward-back thing. But now it can also tumble. It can spin end over end, or it can rotate like a propeller. That's two brand new ways to move, two new rotational freedoms. So we add those to the original 3, and that brings its F value up to 5. And right here you can see the difference so clearly. The single atom, it's stuck with just 3 ways to store energy. But the dumbbell-shaped one, the diatomic molecule, it unlocks 2 brand new ways to hold on to energy, just by being able to rotate. It's like it has these extra slots to put energy into. And that makes all the difference. But wait, there's a plot twist. That dumbbell analogy, with the rigid bar connecting the 2 atoms, it's not always true. When things get really, really hot, that bond stops acting like a stiff rod and starts behaving more like a spring. It can actually stretch and compress. And this vibration, this stretching motion, actually adds 2 more degrees of freedom. You get one for the kinetic energy of the motion itself, and another for the potential energy that's stored in that stretched bond. So you add those 2 to the 5 we already had, and that bumps the total F for a really hot diatomic gas all the way up to 7.
Okay, last case study. Let's look at polyatomic gases. As the name suggests, poly means many. So these are molecules with 3 or more atoms. Think things like water vapor, H2O, or methane. They've got these more complex, kind of 3-dimensional shapes. So, just like everything else, it gets those 3 degrees of freedom from moving through space. No surprise there. But here's the cool part. Because it's not a simple straight line like the dumbbell, it can rotate around all 3 axes. The best analogy is an airplane. It can pitch, it can yaw, and it can roll. That gives it 3 rotational freedoms, which, when you add them to the 3 translational ones, gives you a total of 6.
Okay, great. So we figured out how to count these molecular dance moves. 3, 5, 7, who cares, right? Well, this is where it gets really cool, because this one little number, F, turns out to be one of the most powerful tools in all of thermodynamics. You could almost say it's the one number to rule them all.
And the reason why is because of this really beautiful and simple rule called the law of equal partition of energy. Basically, it just says that nature is incredibly fair. When you pump heat into a gas, that energy doesn't play favorites. It gets split up perfectly and equally among every single available degree of freedom.
Each dance move gets the exact same slice of the energy pie. And once you know that, it leads to this stunningly simple equation. The total internal energy of a gas, which we call U, is just F divided by 2 times a couple of constants. That's it. So if you know F, if you just know how many ways a molecule can move, you can calculate the total energy packed inside that gas. It's incredibly direct. And this is the big payoff. This number F also tells us a gas's specific heat. Basically, how much energy you need to pump in to make it hotter. Now think about it. A gas with more degrees of freedom, like the air around us with its F of 5, has more places to stash that energy. It can translate, it can rotate, but helium, with its F of just 3, has fewer options. So when you hit it with sunlight, that energy has nowhere to go but straight into making the atoms move faster, which means its temperature shoots up. And boom, there's the solution to our balloon mystery.
And believe it or not, the power of F doesn't even stop there. It also lets us figure out something called the adiabatic index, or gamma. This is a super important ratio for understanding things like how efficient an engine is, or even, get this, the speed of sound in that gas. And once again, it all boils down to that one simple number, F.
So let's put all the pieces together now. You can really start to see how this one number, F, acts like a master key. Once you have it, it just unlocks all these other crucial properties of a gas, one after another.
This table here just lays it all out perfectly. Just look at that first row for a monoatomic gas. You start with one piece of information. F is 3. That's it. You plug that 3 into the formulas we just saw, and bam, you instantly know its internal energy, its specific heat, and its gamma value. And the exact same logic just flows down the entire table. It's like a complete cheat sheet for any gas, and it all starts with just counting from 3 to 7.
So, let's wrap this up. What are the 3 things you absolutely need to remember? 1. Degrees of freedom is just a fancy way of saying how many ways can this molecule move and store energy. 2. That number is different depending on whether you've got 1, 2, or more atoms. And 3, the most important part, that single number, F, is the master key that unlocks almost everything else you'd want to know about that gas.
And this isn't just some abstract physics problem. I want you to really think about this. How do engineers design a super efficient jet engine or calculate the exact fuel mixture for our rocket so it doesn't, blow up? They have to know precisely how the super hot gases inside are going to behave. And where does all that complex engineering start? It starts right here, with something as simple as counting those tiny hidden dance moves of a molecule.